Chapter 2, Measurements and Calculations. Unless I should ask, since we've only got one person attending, if Amr has a question or concerns. Otherwise,
No, I don't.
okay. All right, we'll jump right into chapter 2. That's just an outline. We'll get to all those topics in succession. So I think I mentioned during chapter 1's discussion the concept of measurement, where it's a quantitative observation. And measurements always have a number and a unit of measure. Without the unit, the number doesn't have much meaning, except for very few rare occasions where you have dimensionless numbers. And in that case, you have to know where the number came from in order to use it properly. But we'll discuss that one at a future time. Right now, we're talking about measurements that have numbers and units of measure to go with them. And the examples on the right-hand side of your screen are 1 centimeter. Right? It gives you a representation of what a 1 centimeter would look like. And then 1 millimeter below it is a smaller measure. Centimeter means 1/100th of a meter. Millimeter means 1,000th of a meter. So if you compare the two, you find that definitely they're smaller than a meter, but if we want to compare the centimeter and the millimeter, what's the difference between the two? Well, the difference between a 1/100th and 1,000th is a factor of 10. So a millimeter is 1/10 of a centimeter. All right. Scientific notation. Some numbers, even if we pick the units correctly and to give us a manageable size number, sometimes those numbers get very, very large or very, very small. In this example, we have a very large number, 93 million. Now, they didn't just pull that number out of the thin air. 93 million is, without its units, if we put miles behind that as units, that's the distance, the average distance of the Earth to the sun in miles. If we used a different measure, like kilometers, it'd be about 150 million kilometers. But it's the same distance, just different measurements. Now, if we want to express this large number in a more manageable fashion, we can use what's called scientific notation. And let me pick a different number so I won't just be regurgitating what's on the screen. Let's pick, let's pick the kilometers. How about that one? Kilometers distance. What we're doing in scientific notation, and by the way, your book may mention exponential notation, and it may even equate exponential with scientific. They have one thing in common. We are taking the large part of the number and storing that value in a power of 10. Because in the decimal system, that's ones, tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions. And each time we move one to the left, we get another power of 10. So if we move again to the left, we get another one, right? 2, 3, 4, 5. Say we only move 5 over here, right? So we stop right there, and this becomes 5. Then what's left over is 1,500 times 10 to the 5th. That's exponential notation. The scientific notation is a special case of exponential, And it requires that this part of the number, this is the coefficient. The coefficient has to be between, has to be less than 10 and greater than 1. So we'd have to move 1, 2, 3 more. And we would say 1.5 times 10, 3 more, the 8th. So this is scientific notation for that number. They're exactly the same number in a different format. All right. Okay, what happens if your coefficient is 10? So what if I need to get my eraser out? What if instead this was a 0? Okay. Then, and we only moved to this place right here. Well, that would make this 7. And that would make this 10. This number has to be less than 10. So we need to store more information from this one in that location. So we would say 1 times 10 to the 8th. And we're going to talk about why I just threw away those zeros. There's a reason for that, and we're going to get to it. Okay. This, of course, this exponent is positive if this number is huge or is big. But if the number is very small, we can store up powers of 10 in the negative format also. And I think I've got an example coming up. Let's see. Yeah, if you move the decimal point to the left, you store up positive powers of 10. If you move the decimal to the right, you store up negative powers of 10. There's an example of that. The whole point of doing this is to make the number more manageable. So if I pick a number, say, like that, and I want to make it more manageable, now the decimal would have to move to the right to create a coefficient between 1 and 10. So if I move it 3 places, then now this power becomes -3. And the coefficient is 7.0532 because now the decimal is not here, it's there. Okay. Oh, we also need to be able to go the other direction, right? This is called standard notation, where you don't have any powers of 10. And sometimes we need to go from here to here. So when it's a negative number here, and we want to move the decimal, we move it 3 to the left to go back to where we were. And of course, with positive powers of 10, we move the decimal to the right. Okay, which of these expresses 7882 in scientific notation? 7,882. We don't see a decimal point there, but there's an understood decimal here. Right? So it would move 1, 2, 3 to give us 7.882. And the power of 10, since we moved this direction, we stored up ones, tens, actually tens because we're moving from ones to 10, tens, hundreds, thousands. So we move 3 places to the left. That power of 10 is 3. So there's your answer. Now, if you're familiar with this procedure, I'm probably boring you, but some people may not have been introduced to the concept before. That's why I'm taking the trouble to do it. For this one, we move the decimal to the right. How many places? Well, let's see. 1, 2, 3, 4, 5 places gives you 4.96 as your coefficient. And we moved 5 places to the right, so that's 10 to the negative 5. All right. Just to reiterate, we need the number and the scale unit now. We've just been working with numbers up to this point. Now we need a scale unit so we know what that number means. And examples on this slide are, the first one is grams. That's just a single unit of mass. But you can have complex units. The example below that is a unit of joule seconds. That's probably a derived value. If you multiply a number that has joules, say a number that has joules as its unit of measure, and multiply that times some other number that has seconds as its units of measure, whatever you do to the numbers, you also do to the units. So we multiply x times y, and then the units become joule seconds. All right. When scientists talk to one another, they need to agree on the language. And there are lots of rules, of course. One of those that I've encouraged you to start memorizing now is the symbols for elements. And I gave that to you in the first class. You don't need to know that until the second exam, chapters 3 and 4. But the sooner you get started, the easier it's going to be to memorize all those symbols. One of the other main agreements that has to be made among scientists is, what are standard units that we apply to these numbers? Right? Sometimes we're talking about mass, sometimes length, even time, temperature. We need to agree upon what that means so that when I publish a paper and it says 25.7 kilograms, anyone who reads it knows exactly what I mean. And they can reproduce it themselves if they want to take my experiment and try to reproduce it in their laboratory. So these fundamental units are agreed upon standards by the international community. And SI stands for International System, only the letters are backwards because this is French. The kilogram is the standard of mass. And the kilogram is actually a mass of platinum and iridium alloy, which is very resistant to corrosion. And it's a certain size, and it's stored at constant temperature. Used to be in a cave in France under a double bell jar with argon in it. And if you wanted to standardize your kilogram against the standard, you send it to them, they compare it, and they tell you what your kilogram actually, the mass of your kilogram compared to the standard. Now, you'll notice that this kilogram is a derived unit from grams. Grams are inherited from the Middle Ages, from alchemists. The gram was already established as a mass, but the gram is too small. If you have a scratch on it, a fingerprint, anything like that, it has a significant percentage deviation on the actual mass of the gram. So the solution for that was, besides making it out of a resistant alloy, is to make it bigger. So since the gram was already established, we just multiply it by 1,000. Now we have a mass that's about that big. And it's it's more resistant to deviations. So that's why the kilogram is the standard and not the gram. The length, the meter is a standard length. It was derived from the Earth, right? So here's the equator, here's a pole, and here is Greenwich, England. Okay, the distance from here to here through Greenwich on that longitude is a certain value. And whatever unit you pick, we take that and we subdivide it into smaller units until you get something that's manageable. So when I hold my hands out like this, that's about a meter. So once that was agreed upon, a platinum iridium bar was constructed, actually several of them, constructed to represent that meter. And it was stored in that same cave in argon gas. Nowadays, though, we don't have to depend on those platinum iridium bars. Now we have devices that use laser light of a certain frequency, and the device will generate a meter distance very accurately using laser light. The only problem is the equipment is very expensive. So only a few labs in the world can afford to have that, but it does free you from having to send your meter back to France and have it standardized. Okay, now for time. Time was also inherited, but the unit time seconds is derived from astronomy. It's an astronomical unit. So all the committee had to do was to say, what is that standard? I mean, what do we call a second? And that measurement is then the standard. And now we use what they call atomic clocks. It's based upon the decay rate of a certain radioisotope. And that tells you what the standard second is. And everything else is derived from that. Temperature required some fancy footwork, so to speak. And we're going to talk about temperature in just a few minutes in more detail. But the Kelvin is the standard temperature unit. As it happens, the Kelvin unit is the same size as the Celsius unit. So the whole world outside the United States uses Celsius for everything. Scientific research, everyday measurements, weather, so forth. In the United States, we tend toward Fahrenheit for weather and some other things. And then the scientists stick to Celsius. And actually, Celsius can be converted into Kelvin. The advantage to Kelvin is the 0 point. For Celsius, the 0 point, of course, is the freezing point of water. So that means any temperature below that is a negative value. And that can really mess up your calculations if you try to use Celsius in a calculation that needed temperature. Goes from positive to negative, can't have that. So Lord Kelvin came up with this system where he said the 0 point is absolute zero. There's nothing below that. So that way, in the Kelvin system, all the values are positive. I'll discuss that a little more later. The electric current standard is the ampere. We are not likely to encounter the ampere in this course. Right? There's just not enough time. We don't go into that much depth. But if you're interested, the ampere is derived from current, which we represent with I, divided by time. And that happens to be coulombs per second. A coulomb is a measure of charge and a second time. So What you're saying is if you have an amp, say 1 amp, that means in this conductor, at this point, there is 1 coulomb passing that point in that conductor every second. All right. And then one I know we're not going to get to is oh, wait a minute. It's not there. A measurement of luminosity, the candela. I didn't put that one in there. But we are going to introduce the concept of the mole later. The mole is a measurement of numbers of things. It's a very large number. 1 mole, the abbreviated form, equals 6.022 times 10 to the 23rd things. For our purposes, that could be atoms, molecules, ions, usually. And there'll be more to say about that later. Now, if these units, these standardized units, the fundamental units, are not useful for making a measurement, say if I wanted to measure the distance between Beckley and Charleston in meters, that would be a huge number because the meter's only that long. So we can modify the meter with a prefix that makes the number that we measure more manageable. It just simply changes the size of the unit. And if I were doing that measurement from Beckley to Charleston, I would probably pick the kilo, the K. That's times 1,000. So kilometer is 1,000 meters. Now that's my unit. Let's see, what would the distance between here? It's about 50 miles, depending on where you go in the city, about 50 miles. And the ratio is about 1.6. So maybe 80, 85, 82, 3. Let's just say 83 kilometers from Beckley to Charleston. That distance in miles, we were saying was 50 miles. Now, the distance between here and Charleston is not different. It's the same distance. It's a physical quantity. We just changed our standard of measure from miles to kilometers. So these two are actually equal values. They're equal to one another because we're measuring the same distance. Notice what happens. The mile is larger than the kilometer by about 60%. Right? So if the unit gets bigger in our conversion, if we go from kilometers to miles, the unit gets bigger, the number gets smaller. That always happens. You can take that one to the bank. And that's just a rule of thumb that helps you catch any errors that you might be making in calculations. Okay, so there are other prefixes. The kilo is 1,000 times. Right? The deci is a tenth. So we went from making the unit bigger to making the unit smaller. Mega is a million. Centi is 1/100th of. So a centimeter is 1/100th of a meter. So if the meter is this big, the centimeter is about that big. Millimeter is 1,000th of a meter. A micro or micrometer would be 1 millionth of a meter. We're getting pretty small now. Need a microscope to see that small. A nano, 1 billionth of say a meter, or it could be any other unit. Nanometer, or which is abbreviated in M, is extremely small. And there's a whole industry of nanotechnology that sprouted up. There are other units of measure, but notice, I want to point this one thing out. Little m here, excuse me, little m for millimeter. That's 1,000th of a meter. If you make the mistake and write this, you're saying 1,000,000 meters. That's a megameter. So be careful about the case of all the letters that you use. All right. So this is a comparison of modified units with prefixes. And just notice the relationship of each one of these, right? If we start with the meter here and go to kilometer, that means the unit of measure is now 1,000 times bigger. Or if we go to the millimeter, it's 1,000 times smaller. So how many times bigger is the kilometer than a millimeter? All right. If we have to go 1,000 times to get to a meter from a millimeter, and we got to go 1,000 times more to get to a kilometer, we've actually moved 1,000 times 1,000, or 1,000,000, which means the kilometer is 1,000,000 times larger than a millimeter. Okay. All right. Volume is not a fundamental unit. Right? It's a derived unit from length. We simply take height, width, and depth, multiply them together, and that gives you volume. So if the standard unit is a meter, then we get a cubic meter. And that's what we're representing up here on this blue figure. That's a cubic meter. If we subdivide each of the measurements, length, width, and depth, into 10 pieces, we get a decimeter on the sides. If we stop and look at 1 decimeter and cube that, we get a cubic decimeter. We give that a special value. A cubic decimeter is equal to a liter. Okay? Now, liter is always a capital L. If you see it written this way, for any reason, that's not a liter. I don't know what it is. It's just an L. But if we want to modify this unit to make a smaller unit, then we might put a milli in front of it. Milliliter. And sometimes you'll see it written like that. That is wrong. That is not a milliliter. And if you write it like this, guess what? You got a megaliter, 1,000,000 liters in that unit. So be careful with the cases of your letters. Okay, so we've identified a liter in relationship, volume of liter in relationship to length, our fundamental unit. Now, if we take the liter and we divide those sides again in tenths, then we get 1/10 of a decimeter is a centimeter. So if we focus in on that yellow centimeter on a side, on each of the sides is a cubic centimeter. A cubic centimeter is 1 milliliter. Okay? In the medical profession, if you see some old measuring devices, they might be in terms of cc, cubic centimeter. In years gone by, it was easier to label things with a cc than to put a power on it, right? Centimeters cubed. Now I think Most medical devices in volume use milliliters as their measure. But notice 1 cubic centimeter is exactly identical to 1 milliliter. And it takes how many milliliters to make a liter? Well, if a milliliter is 1,000th of a liter, it'll take 1,000 of them to make a liter. All right. Mass, here we go. Mass is a measure of the amount of a substance. So if I have a kilogram of gold, I've got a certain amount of that gold. Now, if I were to take it to the moon, it would be the same amount. It would still be 1 kilogram. But on the moon, it would weigh less. So I'm going to draw a distinction between those two in just a minute. There's your SI unit. And we can equate certain units. Right? In this case, we're saying that 1 kilogram of substance is equal to 2.2 pounds. Now, there's a problem there because kilogram is mass and pounds is weight. It's a force. Right? So we have to stipulate that 1 kilogram is equal to 2.2 pounds only at the surface of the Earth. And we could go the other direction. Now, how do we get 454 grams equals a pound? Well, let's see. I'll show you how we got there. If we say that 1 kilogram equals 2046 pounds, and we want this to be 1 and still retain the equivalence. But we know that the unit we want to go for is the gram. So let's say, what is this equal to? This is equal to 1,000 grams. Right? So now we have this equal to that. So how do you turn this into 1? You divide both sides by that number. Okay? This becomes 1. And this gives us another value, which should be 453.59. 53.59 grams equals 1 pound. Another skill that would be useful, excuse me, that would be useful, especially if you're checking yourself to be sure that you're making the correct calculations, is to learn the technique of estimation. If I were to take this 2.2 into 1,000, I would say, okay, if it was 2, it would be 500, right? Half of 1,000. But it's a little bit bigger. It's 2.2, so it should be less than 500. And sure enough, it's less than 500. That estimation helps me confirm that I didn't make a calculation error. Rather than just punching it into my calculator and believing what the calculator tells me. Calculator is nothing more than a computer. And one of the famous sayings from the beginning of computers was garbage in, garbage out. If you put the wrong numbers into a computer for a calculation, it's going to give you an answer, but it'll be the wrong answer. So being able to estimate the answer that you expect helps you confirm and avoid those types of errors. All right. Choose the statements that contain improper uses of commonly used units. Doesn't make sense. Okay. Let's see. Let's make some room here. 1 gallon of milk is equal to about 4 liters of milk. Well, We have to know what a gallon of milk is worth in terms of liters. And I happen to know that because I read labels in the grocery store. Even if I'm not going to buy the stuff, I'm just curious. So I'll pick up something and look at the label and see what's in it, what's its analysis, what the analysis of it is, and so forth. If you pick up a gallon milk, nowadays, measurements on the shelf in the United States will have both imperial units, they say, or I don't know what else to call them. Imperial units is good. They'll have those units, and they'll also have metric units. So pick up a gallon of milk, and on the side it says 3.8 liters. So the first statement is true. How about 200-pound man is a mass of 90 kilograms? Well, we just looked at the conversion factor there, right? 90 kilograms would be about 2.2 times that. So 2 times 90 is 180, and then 0.2 is maybe another 18. So yeah, 200-pound man has a mass of about 90 kilograms. That's true. A basketball player has a height of 7 meters. How much is a meter? Meters about that long. Put 7 of them end on end, and that basketball player could not stand up in this room. That's not reasonable. So that's the first one that's not proper. A nickel is 6.5 centimeters thick. Well, how much is a centimeter? Well, it's a 100th of a meter, which is about like that, right? So 6.5 of those would be like that. So are nickels that thick? No, they're not. So that's the other one that's false. Now, here's a very, very important concept. Scientists realized early on in the modern era that whenever you make a measurement, there's always it could be a known or an unknown uncertainty involved. Okay? Your measurement is not exactly what you think it is. So there was no way around this uncertainty. Okay? And I'll make mention of different types of errors that can be made that generate the uncertainty. But we needed a way to harness the uncertainty so we could still use the values that we determine or measure. And then in calculations, what do we do with them? Right? So that we're honest. Science has, from the beginning, tried to be honest with understanding the natural world. Now, there are always some, science is a human invention, so humans are going to try to cheat. And one of the purposes of science is to weed out the cheaters. And I'll mention how you do. Well, actually, I did already mention that in the first chapter when we talked about the scientific method. But this uncertainty has to be harnessed. We have to understand as much as possible about it so that we can account for it, sometimes even control it. So the first thing we do is in any number, like this number, scientists have an understanding amongst themselves. Where does the uncertainty lie in that number? We're claiming that these digits are certain. That is, there's no variation in those first 3 digits. The last digit to the right is always the uncertain digit. So if you're reporting a value and you want other scientists to understand what you mean by that number, always be sure that the last digit is uncertain. Another word for that is a guess. Maybe an educated guess, but it's still a guess. All right. So what does that look like with a measuring device? Well, here's a ruler, and it's marked off in centimeters, and what's between the centimeters, tenths of a centimeter, is a millimeter. So if we're measuring this tack, it looks like on the top left one, it's maybe it's between 2 and 3 centimeters. Okay, and then we blow it up, and we find that the other one is between 8 and 9 millimeters. Okay, so it's between 8 and 9 millimeters. Then we blow it up some more, and we see that we're somewhere between those two. And we find out that that's, well, in this slide, this is not a good slide, I just realized, because it puts the point, the end of that tack, directly on a measure value, halfway between 8 and 9. So we would say that that measurement is 2.85. But the 5 is not uncertain, because there's actually a line there that says this is 5/100ths of a centimeter. So what I'm arguing is, if we say this, if we say that's our value, then we're going to assume that that 5 is uncertain. But it's not. There's a line on that measuring device right there that says 5. So what we have to do, if we think it's right on that 5, then our uncertainty is in the next digit. There's my uncertain digit, right there. A better example would put the end of that pin between the 5 and the 6, or between the 3 and the 4, and then we would estimate the last one. But this estimate places the uncertain value at 0. See, that's the problem. We actually have a value for 5, but we're saying if we write it that way, then I'm going to assume that that 5 is a guess. Okay. Now, the next step is to understand what that measurement means in terms of two possible interpretations. The first one is accuracy. Accuracy requires that you either know the true value when you're making a measurement, or you know an accepted value. That's more likely. An accepted value would be such and such, and your measurement would either be close to it or far away from it. If it's close, it's accurate. If it's far away, it's not accurate. Precision, on the other hand, requires that you make 2 or more repeated measurements of the same phenomenon. And then you look at the distribution. If the distribution of your measurements are very close, each one is close to the other one, then you have a precise measurement. If they're far away from each other, they're just all over the place, then you have a not precise measurement. And I have, we're going to use, let's see, what are we using? We're using a gun target. Okay. So this one, what would this one be? Notice that there's a wide spread on your impact points for the bullets. That would be not precise. But if you average all those values together, they end up on the bullseye. This would be an accurate group of measurements. Accurate, but not precise. Let's look at another example. Here we have a closer grouping. So I would say this grouping is precise. But if we take the average of those values, it's not on the bullseye. So this will be not accurate, yet precise. How about this one? This is the ideal. You've got a tight grouping on the bullseye. That is both accurate and precise. If you're sighting in your scope on your rifle for hunting season, you go to the target range, you put your target out there at 200 or 300 yards, and you fire at the target, and you get this pattern, then you don't have to change your scope at all. It's on target. But if your scope is, say, let's see, no, that's not a good example. If your target, your bullseye is here, right? And you have a grouping out here like this, right? That's precise, but it's not accurate. So what do you do with your scope? You do what they call dope your scope. You change elevation to bring it down and windage to bring it left. And then you fire 3 or 4 more shots and see where they land. If they land here, then you've done your duty, your scope is sighted in, and you can go hunt your deer. This last one does not give you an average value on the bullseye, and it's a widespread. This is both not accurate and not precise. So those are the 4 possibilities for any group of measurements. Now for accuracy, you can say accurate with 1 measurement, but precision requires more than 1 measurement. And usually more than 1 measurement is used for determining accuracy also. Okay. And then the last statement on this slide is has to do with the accuracy of a measurement in which you are making a measurement in sequence with different tools. The accuracy of the overall measurement is only as good as the least accurate device in the sequence. It's like the weakest link in a chain, so to speak. Now, I talked about controlling, understanding, and controlling how we deal with uncertainty. And that takes us to the topic of significant figures. If you've had a math class, you probably discussed significant figures, but we're going to go over it again here just for posterity's sake. There are rules. And when we say significant figures, those are the figures that we keep. Those are the ones that have a bearing on our measurement or any calculations that we do with our measurements. So we look at the zeros first. Any non-zero integer always counts as significant. Excuse me, we look at the non-zeros first, pardon me. Any non-zero digit in a number is significant. All right, so if we have this number, there are 4 significant figures. Then we go to zeros. There we go. There are 3 types of zeros. There are, and we start with the decimal point. Zeros to the left, and 2 rules for zeros to the right. So our zeros to the left, zeros here, and zeros here. I'll tell you what those are in a minute. Zeros to the left never count. They are never significant. Example, 0.048. That only has 2 significant figures. Oh, and I might add, when you write a number, if it has a decimal to the left of that number, if you write that number like this, that's wrong. You have what I call an orphaned decimal. This decimal must always be bracketed by another 0. The reason we do that is, at least on this side of the ocean, if you put that number in a sentence, it's easy to get that decimal confused with a point, a period at the end of a sentence, or a period anywhere in the sentence. So we put that 0 in there to protect it. All right. So the point of that is, if you were in one of my courses, well, if you have to answer a question and the answer you give is a decimal like that, and you leave that 0 off, I'll count it wrong. Okay, now we have captive zeros. We did this one. This one's captive zeros. that is between, say, a 5 and a 4. And it can occur in a number that doesn't show a decimal or one that does show a decimal. Let's see, our example, 16.07. That number has 4 significant figures because the 0 is captive. It's between 2 significant non-zero numbers. That's redundant. Non-zero numbers are always significant. But that 0 is significant for at least one reason. Without it, we don't have the same number, right? It would be like 16.7 or 1.67, or take your pick. It wouldn't be 16.07. And then the last type, maybe we did this one. The last type is zeros to the right, trailing zeros. Now, those zeros have conditions. If those zeros are not, if the number doesn't end with an explicit decimal point, then those zeros are not significant. So this number would only have 2 significant figures. But if we put a decimal here, we would have 5 significant figures. That's an explicit decimal versus an implied decimal. Every number has implied decimals, and even if we don't show them. But explicit decimals have a special place in this set of rules, right? So that has 4 significant figures. This one doesn't have any trailing zeros, right? So we can't say that. But if we did put a 0 out here, now it would have 3 significant figures because there is an explicit decimal in that number. And our example here is 150 with no. Now, if you intended for the third digit to be the 0 to be significant, then all you have to do is put a decimal there. Now that 0 is significant. And the last class of numbers are called exact numbers. Exact numbers have infinite number of significant figures. Now that's important for calculations because of the rules for calculations. If you have an exact number in your calculation, you can ignore its significant figures. It has no bearing on the outcome. And I'll show you what that means in just a second. These numbers could be equalities, like this, where 1 inch equals 2.5 centimeters, and we have established that as an equivalence. That means that 2.54 centimeters has infinite significant figures. Or counting numbers, right? It doesn't make any sense to say 9.5 pencils. All right. Wait a minute. I thought we already talked about that. Well, exponential notation. All right. Okay. So I need to work on my slide set, I think, because this is redundant. Oh, in relationship to significant figures, notice that if we have that number, let's pick a different number. Say we have 5, 6, 7, 0, 0, like that. That has 3 significant figures in it, right? If we write that as scientific notation, not exponential, right? This is exponential that you're looking at there, but it's not scientific. But if we use scientific notation and implied decimal is here, we go 1, 2, 3, 4. 5.67 times 10 to the 4th. Notice I didn't carry the zeros over because they're not significant. In a number that has been rendered as a scientific notation, loses the non-significant zeros. So this says we have three significant figures in that number. This says we have three significant figures in that number. Now, what would I do if that's the case? Now we get 10 to the fourth, and this coefficient is actually 5.6700. That preserves all five significant figures in this number because of that decimal. Or if we take something like this, as it is there, and we say 4.80 times 10 to the minus 1, 2, 2. So I retain the zero because it is significant. Now, we're going to all this trouble to study significant figures because of what we're going to do next. We're going to use what we know here in calculations so that the result of calculation is trustworthy in terms of significant figures. Okay, first, though, we need to know how to round numbers. There are different ways to round numbers. We're going to use probably the earliest and the one that's easiest to remember. If you have a number, let's take this number, let's modify that one. 54370, 0, like that. And say I need to round that number to the hundredths position. Excuse me. No, let's go further. How about the 10,000th position? Ones, tens, hundreds, thousands, 10,000. Right here. I need to round it to that position. Well, actually, I want to keep this number. I want to keep these two. But I need to know what effect does this part of the number have on that number when I do my rounding. So we're going to use the rule. If the number to the right of the position you have to round is less than 5, then that goes away. And we keep the number. But if that number is 5 or above, then this one goes up 1. And the rest go away. So now we've rounded it to that position. 5 and above, round up. And you don't say round, 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 round. You simply go first digit to the right of the position that's rounding and make your decision. 5 or greater, round up. Less than 5, round down. Okay? That's all we're saying with these rules. Now, in a series of calculations, we have two sets of rules. We either multiply or divide the numbers, or we add or subtract. One rule is multiply, divide. The other rule is add, subtract. Multiply, divide is really simple. If you have two numbers, say that you multiply them together, you simply restrict the answer to the same number of significant figures as the least number in the operators. Right? So for this example, 1.342 times 5.5, in your calculator, say it spits out a number 7.381. Your calculators don't know about rounding, right? They just tell you as many decimal points as you program into the device. I have mine set up to display 8 decimal points, and then I'll do rounding. So with this number, this calculation, we have 4 significant figures times 2 significant figures. So the answer can only have 2. So we take the answer that comes from our calculator, And we say two significant figures counting from the left, 7 point, and you stop at 3. You look to the right of 3, which is 8. That means 3 has to be bumped up to 4, and the rest goes away. And notice we don't keep the 8 or 1, right? Because they are not significant anymore. They're not zeros, but in the calculation, they're not significant either because we can only keep 2. All right? And that works for division as well. Now, that previous slide mentioned multiple calculations. If you have multiply and divide in a sequence, right, multiply, multiply, divide, divide, multiply, divide, they're all multiply, divide. Do the calculation all the way to the end. Then look at the operators that you've used. Take the least number of significant figures out of that whole set and apply it to your answer. The reason we do that is if you round at every operation and you round up each time, your answer is going to be too high. Or you round down each time, your answer is going to be too low. So for this operation, since it only depends on the least significant figures, you can multiply, divide all the way to the end and then apply the rule. And that avoids rounding error. Okay, the other rule is add, subtract. This takes a little explaining. When we add, subtract, the key is to line up your decimal points. So if you have two numbers that you want to add, like this, 23.445 and 7.83, you line up the decimal points. And then you add the whole thing through. And then you look at the least number of decimal places. So that would be 0.83. So you can only keep 2 decimal places in your answer. That means the 7 must be rounded up to 8. Okay? Subtraction, same rules. Let me see. I got an idea and okay. Let's hold on that thought. Let's say you have, I'm going to use 2, 3, 4, 4, 5, and 7, 8, 3. 7, 8, 3, 0. I want to add those together. Okay. Now, how do I know where to stop? Well, let's add them together first. 5, 7, 12, 11, 3. Okay. You got your decimals lined up, but there are no decimal places to the right of the decimals. So where do I stop? You go to significant figures. The position of significant figures is limited by this one because that's not significant. So that's where we round. Right? 3, 1, 2, 8, 0 with no decimal point. That means these are significant, that one's not. Okay. We're just illustrating the point here that if you make 2 measurements of this liquid in the graduated cylinder on the left and the graduate cylinder on the right, the more accurate cylinder is the one on the right. The least accurate is the one on the left, and if you combine those volumes and report a value, it must be limited by the accuracy of the least accurate device, which is the cylinder on the left. So the idea is 3.1. Why did I put 3.1? That's, total volume. So 2.8 and then 0.8. The point of the slide is the precision and the accuracy. Actually, accuracy is the better term. accuracy of your outcome is limited by the least accurate device. Okay? Before we get into dimensional analysis, let me talk about the different types of error. There are two types of error in any group of measurements. There's what we call systematic error and random error. Right? Systematic error is like that rifle that you're trying to sight in with your telescope, your telescopic sight. And if you fire it at the target, it hits off target, same place every time, or almost the same place every time. That's the same error each time. Sends it this way, this way, this way. Systematic error can be controlled. If we know that our measurement is off by a factor of 0.01 whatever, then we know that the true measurement is actually minus that value. And we can account for a systematic error. Random error, we have no idea why the error is random. It could be anywhere. So what we have to do with random error is make multiple measurements. We call them replicates. We replicate the experiment, replicate the measurement, and then we take an average and we draw on statistics to tell us just how far afield our measurements are from one another. And we don't have time to talk about that now. We use concepts like standard deviation, for instance, which is a calculation that statisticians use to tell them just how much variation there is in the measurement. But it's still random, right? And we cannot control random error. Okay, now to dimensional analysis. Most often, dimensional analysis is used in the context of converting units. So when you make a measurement and it has a unit, you don't like that unit, you want to go to another unit. You analyze the dimensions to see what I need to do to convert from this unit to that unit. And this can be multiple steps also. Conversely, you can solve problems by saying, if the question says it wants an answer in a certain unit of measure, you can work back through the problem and say, all right, in order to get there, I need this information, and I need to multiply, divide, add, subtract, whatever, to get to that point. A lot of chemistry problems can be solved by dimensional analysis. If you understand the chemistry and you don't violate any laws or rules pertaining to that branch of chemistry. All right, so how do we do a unit conversion? You need some type of factor that is derived from an equivalence that relates those two units. For instance, 12 inches equals 1 foot, right? So if I have a ruler, I know that it's 1 foot, but it's also 12 inches. The physical distance from one end of that ruler to the other didn't change. Only the units of measure changed. And notice, when the unit gets bigger, the number gets smaller. But that equivalence allows us to make the conversion. I'm going to show you how in just a second. Actually, I'm going to prove to you why conversion factors work. Okay? Those are just steps. Steps in conversions. We need an example. So let's say a professional golfer has to putt the ball from 6.8 feet away from the hole and get it in the hole. And any professional golfer worth his salt will sink that putt every time. So how many inches are required for this putt? Okay. First, you need an equivalence. You need to know that feet equals so many inches because we're converting from feet to inches. So we need to know that equivalence. And if we say 6.8 feet, we got to multiply it by something to equal inches. Right? So we could multiply it by 1, right? Mathematics allows us to do that. Anything multiply 1 didn't change the number. It's the same. But that doesn't get us our answer. So we need some way to get rid of that feet and give us inches. And remember, whenever you operate on 2 or more numbers, you have to do the same operations on the units. So if we want to get rid of that feet, we need feet in the denominator to cancel it, don't we? Right? And that means we need inches up here to remain and give us our value. So what if we take this equation and divide both sides by, let's see. Yeah, that'll work. Excuse me. That'll work. 1 foot. We divide both sides by the same value. That's allowed in math. This now becomes 1 because that cancels, and 1 divided by 1 is 1. So now we have this expression equal to 1. Remember, that was 1. So let's substitute this one right here. 12 inches, 1 foot. That gets rid of feet. 6.8 times 12 will give us our answer in inches. $82 inches. It's the same distance. 6.8 feet is 82 inches. We simply analyze the dimensions of our problem to arrive at an answer. Does my answer make sense? And do we have the correct number of significant figures? Well, this has 2 significant figures, and this, all conversion factors are exact numbers. This has no bearing on the outcome in terms of significant figures. So 2 significant figures here, 2 significant figures there, we're good. Now, if we have a 4.50 pound iron ball, and we want to know what is that in terms of grams? Well, we do have a conversion factor for pounds to grams because we calculated it earlier. 454 grams equals 1 pound. But suppose we don't know that. And we do know that 1 kilogram is 2.2046 pounds and 1 kilogram is 1,000 grams. We can do a chained conversion. And this is what it looks like. 4 pounds, if we multiply that by this equivalence, 1 kilogram per 2.2 pounds, then the pounds cancel. And we have kilograms now. And now we also have a conversion factor from kilograms to grams, which we put here. That cancels the kilograms, leaves us with grams. And then all we have to do is crunch the numbers, and we get 2.04 times 10 to the third grams in scientific notation. Now, the number of significant figures, the conversion factors don't count because they're exact numbers. 4.50 is 3 significant figures. 2.04 is 3 significant figures. All right, let's see. 10, check my time here. Okay, we're good. So here's another problem. practical problem. You know, if you study chemistry, you study any of the sciences, but we're going to stick with chemistry right now. Not only does the skill set that you learn in problem solving for chemistry, not only does it allow you to solve chemical problems, this thought process can be translated into everyday logical approaches to solving real world problems. And this is one of those examples. Say I want to go, well, actually, New York to Los Angeles. I don't know anybody that wants to go from New York to Los Angeles. But for me, I would go from Beckley to Atlanta because I have people down there. And I need to know, how much money do I need to keep? How much money do I need to have when I leave the house to get down there and back? Say I just got just enough gas to get to the service station before I leave town. So how much gas do I need to put? How much money do I need to spend to put gas in the car to get down there, drive around a little bit, and then put gas in the tank, even on the way and down there to get back? Right? How much money? That's a practical problem. So what do I need to know if I want to end up with dollars? I need to know dollars. What do I need to do over here to get dollars in my pocket and reserve that money for gasoline? Well, you need dollars here, right? That has to be in the numerator because it's going to end up as the last calculation. So what do we know that relates dollars in terms of my driving? The cost of gas, dollars per gallon, right? So we're going to have gallons here, and then we're going to have a value here, right? I filled up my tank yesterday for $2.79, $2.79. Now, it's going to vary from here in Atlanta, so maybe we'll take an average. Say it's $3 per gallon, okay? That means something over here has to cancel gallons, right? These have to be canceled. What do we know about our vehicle that is useful in terms of gallons? Mileage. What kind of mileage does your vehicle get? Right? How many miles per gallon? Right? Let's keep it simple. Let's say you got a pretty efficient car, and on the road, right, you're going to average about 30 miles a gallon. Okay. So now, all I need now is, how far is it down there? Right? And I think to where I usually drive, it's about 435 miles. That cancels miles, gallons canceled. Now we're going to end up with dollars. That's the thinking part of the problem, putting this together. The rest is number crunching. So you put this in your calculator, 435 divided by 30. If you have an algebraic calculator, you have to say equals. And then times 3. And that's how much money you need to get down there. Then you want to double that for getting back. And then you may want to drive around a little bit. So I would pad it with at least 10%. This value times 2 times 10% times 1.1, right, adds 10%. And that's the amount of money I want to have when I start my trip. And I don't spend it on anything else but gas. All right, for the sample answer, New York to Los Angeles is 2,500 miles, and I'm using 25 miles a gallon. This problem is dated. 3.25, $3.25 a gallon, and there's your calculation. You need 325 just to get there. And then we would double it and maybe pad it with, I don't know, 20%. Okay, now we're going to talk about temperature. The agreed upon international standard for temperature is the Kelvin. But there's a history behind that. And that's what I want to look at here. Fahrenheit came first, and it's named after its inventor. I don't remember his first name, but the person that invented the thermometer for using Fahrenheit, and that was the one thing that held things back. We didn't have a reliable way to measure temperature, the heat that's contained in a substance. Fahrenheit was interested in living systems. So what he had to do was create a device that had a liquid in it that would expand and contract as temperature went up and down. And the choice was, well, for a while, I'm not even sure if he used mercury first. He may have used water, some colored water, or alcohol, which is what we use now instead of mercury. But in any event, he needed a liquid that would expand or contract with a change in temperature. And then he needed to set the scale. So Fahrenheit chose living systems as his standard. The high temperature at 100, he said, would be the average body temperature of warm-blooded animals. So he sort of took an average and said, that's 100. Our body temperature is nominally 98.6 degrees Fahrenheit. Cats and dogs are about 102.5. So he had to kind of take an average. But once he established that value, then he needed a 0 point. Well, he didn't have a reliable 0 point for living systems because 0 in a living system usually means death. So he picked 0 as the coldest temperature he could produce. So distilled water and ice made from distilled water plus sodium chloride, salt. So he made the coldest temperature he could, and that's 0. Okay, once he had 0 and 100 degrees, he just subdivided 100 units, and that's the size of your Fahrenheit degree. Celsius, on the other hand, came a little bit later, and he was more of a chemist, a physicist. So he wanted a system that was just easily reproducible. So he said the freezing point of distilled water is 0 degrees on my scale. And the boiling point of water on my scale is 100. But that had to be at 1 atmosphere pressure because they knew by then that the boiling point changes with changes in air pressure. So he had to do it at sea level. And then he subdivided his into degrees Celsius. When you compare the two systems, 0 degree freezing point is actually 32 on the Fahrenheit scale. And 100 boiling point on the Celsius scale is 212 degrees on the Fahrenheit scale. Now that we know that, we can create a formula that will convert one to the other. We have to account for the difference in degree sizes and the difference in the 0 point. And this formula is what does that. Measurement of Fahrenheit temperature is equal to 9/5 of C. This corrects for the size of the degree mark. And this corrects for the 0 point. So that's how you convert from Celsius to Fahrenheit. And if you want to go the other direction, you just plug in that number and solve for the unknown, right? So you need a little bit of algebra. Or you can rearrange the equation. We can rearrange, bring this 32 over here. And then take this fraction across the equals, which flips it. So we would say 5/9 times what's inside the parentheses. And now you can solve for C. Just plug in Fahrenheit and solve for C. Kelvin, on the other hand, came a little bit later in the middle of early part of the 19th century. And there was a lot of interest in the scientific community in thermodynamics. Let's see, how does heat transfer from one place to another? How can we harness that heat transfer to do work for us? That was not just a scientific curiosity; it was an economic reality. Because by this time, the steam engine had been invented, and they were very, very inefficient. So a lot of people were working on this, especially one Frenchman. His name was Carnot, Sadi Carnot, who did a lot of work on it. And Lord Kelvin also was interested in it. And he came up with a system. He realized that the calculations would be garbage if you had any negative values of temperature in your calculations. It would just blow that ship out of the water. So he came up with this system where zero is absolute zero. Now, we'll talk about how he got that value later when we get to a discussion of gases. But once he set that 0 point, and he used the same size degree mark as Celsius, only he moved the 0 point. Now, 0 degrees in Celsius is 273 degrees in Kelvin. Okay, so that means if you know your Celsius temperature, you just add 273 to it, and you get Kelvin. Even if it's a negative number, you'll get a positive Kelvin value. Okay, now if you have to find out what Kelvin is, and you start with Fahrenheit, then you want to convert to Celsius and then convert to Kelvin. It's a two-step process. All right. So this is methods of conversion. You see the Celsius Kelvin on the top. And notice that Celsius and Fahrenheit both have degree mark that I omitted here. Kelvin does not have a degree mark. You don't say degrees Kelvin, you just say number Kelvin. Don't ask me why. It's just accepted. Notice this formula down here. Temperature in Fahrenheit equals 1.8 times temperature in Celsius. 1.8 is the same as 9/5. But I learned 9/5 when I was memorizing this stuff. So that's what I used. Okay. If you're interested in how this formula was derived, then I put this link in here. I think it's still active. And it will tell you how that formula is derived mathematically. All right. Normal body temperature for a dog is approximately 102 Fahrenheit. What's this temperature in Kelvin? So 102 degrees for a dog has to be converted first to Celsius and then to Kelvin. So I think I've animated it. I hope I have. There we go. So that arrangement here will convert to Celsius. 39 degrees Celsius. Then you put it in the other formula, add 273. So your dog's temperature is 312 Kelvin. And by the way, what is 98.6 degrees Fahrenheit body temperature? In Celsius, it's exactly 37 degrees Celsius. Here's another interesting problem. Since this size of this degree is different than this size of the degree, they should intersect at some point, and the number for the temperature in each scale should be equal. So that's my question. At what temperature does degrees Celsius equal degrees Fahrenheit? And you need a little algebra to do that. If those temperatures are the same, we can just make them the same unknown value. Call them X. Right? So if we convert that, if we call those values X, then we get this arrangement. X equals X minus 32 over 1.8. You just solve for X, right? So if we were to do that, I don't know if I've got it animated. Let me see if I do. Nope, sorry. So if you're weak on algebra, this is what it looks like. X minus 32 over 1.8, right? Yeah. Okay. So when we're solving an equation in algebra, you try to get the unknown on one side of the equals and everything else on the other side. So we do need to deconstruct this by moving that 1.8 over here. So the long way to do it is to multiply both sides times 1.80. That cancels this one and puts it over here. Notice that in the denominator over here, it's in the numerator over here. And then we want to get this X over here. So across this thing, what we would do is 1.80x equals X minus 32. We would say subtract X from both sides. Oops, sorry. Minus X. Okay. That would cancel this one and leave us with 32 on that side. What's 1.8 minus 1? It's 0.8. Now, X, we divide both sides by 0.8. Okay, so now X equals 32 divided by 0.8, which is minus 40. Actually, this is, excuse me. Oh, this is a minus, excuse me. That minus is here. So that makes minus 40. Minus 40 degrees Celsius equals minus 40 degrees Fahrenheit. And believe me, that is very cold. One of my first jobs was working for a hotel and restaurant supplier. And we had dry goods that stored at room temperature. We had a cooler where we stored things that didn't have to be frozen. We had a freezer storage at minus 20 degrees Fahrenheit. And we had a blast freezer where we took fresh stuff and put it in the blast freezer and freeze it in just minutes. But everything that's in our storage, no matter where it is, every month we had to inventory it. So they would bring us in at 3 o'clock in the morning, feed us a high calorie breakfast, sausage, bacon, grits, eggs, biscuits to get our heat level up. And then we would all take off and go inventory our products. Well, I was a low man on the totem pole. I was a college student working part-time, so I got to do the blast freezer at minus 40 degrees. So I would suit up, wear big gauntlets, and have a huge pencil that I could hold in those gloves. And I would go into that blast freezer for 10 or 15 minutes and inventory what I could. I come out into the cooler and warm up, and I go back in. So minus 40 degrees is very, very cold. All right, let's talk about density. And the reason I want to talk about density, there's several reasons actually. One of the reasons is I want to draw the distinction between extensive versus intensive properties or values. An extensive property is one that changes with the amount of substance. like mass. If you have more of something, you're going to have more mass. Right? It changes with the amount of substance. An intensive property is one that does not change with the amount. For instance, if I have an iron ball this big and an iron ball this big and measure the temperature, and we put them in boiling water first and then pull them out and measure the temperature. They're both going to have the same temperature, no matter how big difference there is. That's an intensive property. Another intensive property is very often a ratio, like density. Mass per unit volume. Density is mass per unit volume. So if this is grams and this is cubic centimeters, the unit of measure is grams per cubic centimeter. Right? That is an intensive property, density. It doesn't matter how much gold I have, whether I've got a little bit or I have a big chunk, it's going to be the same density, both of them. Doesn't matter how much. The other reason we're going to look at density is for its utility as an equation. This equation has 1, 2, 3 unknowns. If we know 2 of them, we can solve for the third one. Right? If we know the mass of a certain volume of substance, we can calculate its density. If we know the density and we know the mass, we measure the mass of that substance, then we can calculate the volume. Or if we know the volume and density, we can calculate the mass. Now, common units of measure for density are either grams per cubic centimeter, which is by convention for solids. For liquids, we say grams per milliliter. The number for any measurement of density, if we measure like 3 grams per milliliter, that's exactly the same as grams per cubic centimeter. Why? Because 1 cubic centimeter equals 1 milliliter. So it's just convention. Right? It's the same number. All right. Now, in order to calculate density, we need to measure the mass. So we would use a balance. If it's a small amount of substance, we'd use a benchtop balance. If it's a large something, we would use a floor balance, or even if it's a semi-trailer truck, you use a special pad. You drive the truck onto it, measure its mass, and they go on down the road. Anyway, measuring mass is not that difficult. Measuring volume can be tricky. If you have a perfect cube, all we need to know is width, height, and depth, and we can calculate the volume. Or if we have some other regular, something maybe a cylinder, right? We know that height times area is the volume. Okay? But what do you do if you have an irregularly shaped object? And in some of my classes, we use that. We have an irregular, say a chunk of zinc, for instance. It's an irregular shape. Or sometimes I use a cork, a rubber cork. It has a regular shape, but it's a trapezoidal shape, and it's a little difficult to deal with. So how do you measure the volume? Well, assuming your substance doesn't react with water, then you could submerge it in the water and measure the volume before and after. So when you put your object in the water, as long as it's completely submerged, it will displace a certain amount of water, and you can measure the difference before and after. That would be the volume of your object. Suppose you put an object in the water and it doesn't float. What would you do? Well, one way to do it is you take a thread, tie it to your object, and put a lead weight on the other end of it. And then you lower it to where the lead weight is in the water, and you measure that as your initial volume. And then you let it go, and it's dragged into the water. Now it's completely submerged, and you get a difference. Okay. So let's see. Am I coming up on? Yeah, I'm coming up on the end. I hope I'm about finished, I think. Let me check. Yes. Just about done. We should finish on time. A certain mineral has a mass of 17.8 grams and a volume of 2.35 cubic centimeters. What's the density of this mineral? You ask yourself, how do I calculate density? Right? So you need the formula. Density equals mass divided by volume. Then you ask yourself, do I have enough information? Right? What's the question? Density is the question. How do I get there? Well, I see what information is given. 17.8 grams, 2.35 cubic centimeters in the correct units. I plug them in the equation and I get an answer. There's my density, 7.57 grams per cubic centimeter. Remember, units are divided just like the numbers. So grams divided by cubic centimeters is my unit. In the next example, we are given density and we're given volume, right? And we have to be sure that the units of measure are compatible. 49.6 milliliters has the same unit of volume that density has in its unit, grams per milliliter. Because when we rearrange the equation, well, they didn't do it for us. When we rearrange the equation for mass is going to be density, 0.85 grams per milliliter, times 49.6 milliliters. Right? And notice that numerator, denominator cancels and leaves us with grams. That's another way to check yourself. Dimensional analysis. If you're expecting a mass of grams, then your calculation better give you grams. So before you even calculate, crunch the numbers, you can look at the units and see if you got the right units in the calculation once it's completed. And does that agree with what you're expecting? That's good. Now, if we have an object with a mass of 243.8 grams and it occupies 0.125 liters, what's the density in grams per cubic centimeter? All right. So here we have to pay attention to the dimensions. Dimensional analysis. We note against the answer, we've got to use the density formula. But this has to be in grams and this has to be in milliliters. Or actually, cubic centimeters, excuse me. Cubic centimeters. Right? So, grams are good, but liters are not. So how do we find out cubic centimeters from liters? 0.125 liters is how many milliliters? Notice, cancel the liters, leave us with milliliters. Well, it takes 1,000 milliliters to make a liter. But we need cubic centimeters, right? So we're going to cancel milliliters and leave us with cubic centimeters. Just so happens that they're equal, okay? So multiply that times that, you get 125 milliliters. Now, if you know that 1,000 milliliters will go to make a liter, then you can you can go directly from here to here. Remember, the unit gets smaller, the number gets bigger. And all we have to do, this is the beauty of the decimal system. All we have to do is move 1, 2, 3 places. 3 places is 1,000. 1, 2, 3 places, there's your answer. Now we can do the calculation. We just put the grams in here, volume in there, like that. That gives us our volume. We put it in our formula, and we get 1.95 grams per cubic centimeter. In this case, we have copper with a known density, and we have 75 grams of copper. That's the mass. And we're going to put it in 50 milliliters of water. What would be the final reading? Okay, so we're going to use this to find out what's the volume of the copper. Right? The volume of the copper now is mass divided by density, which is 75 grams divided by 8.96 grams per cubic centimeter, and this is grams. So numerator, denominator, that cancels. And notice this cubic centimeters is in the denominator of the denominator, which in mathematical terms is a numerator. So this flips up here like that, and we get, let me get my calculator. $75 divided by 8.96 is 8.37 cubic centimeters. Actually, a cubic centimeter is a milliliter, so we can change that to milliliters. That's the volume of the copper, but that's not the answer to the question. What will be the new reading if we start at 50? This is equal to the initial volume. We want the final volume, and that's equal to 50 plus 8.37. 58.37, or rounded to 3 significant figures, or wherever the decimal happens to be. So that would be, after we do all the calculations, here we go, 58.4 milliliters. That's the final volume. Some problems are very simple. 1 step, maybe 2 steps. Some are more complex. To get to the right answer, you may have to break a problem down into pieces, solve the individual pieces, then bring them together to give you your final answer. And this is one example of that. And we're done. Okay. Sharing is stopped. Okay, that's good. All right. And we got 3 minutes to spare. Any questions? About anything, actually. Doesn't have to be about the class we did today. About anything. And for Amr and everybody else that is going to watch this video, you should already be started learning the symbols that I showed you in the first video. Symbols for elements. You need to memorize those. If you don't have those memorized, then you can't learn the language of chemistry. That's your alphabet. All right, just a word of warning. Okay, we're done for today.